Good morning, Ramdar sir.
Good morning, Dr.
Good morning, sir. Good morning, Dr. Prashad ji.
Very good morning, Dr. Malik. How do you do?
We are fine, sir. And how are you?
Thank you.
It's our pleasure to see you here.
Yes, certainly it's a pleasure. Although a physical meeting is far better, and the online can never match that, but still it's good to see people at least virtually.
Yes, sir. Yes, sir. Yes, sir.
Namaskar, Japjit Singh ji.
Sir.
Yes.
Sir, he is
Dr. Professor Singh, sir, head of this.
Sorry, there is some problem with the audio.
Yes. There is. That's there.
Okay.
Sir, he is our head of the department.
Very nice to know, sir. Good morning to you.
Good morning, sir. Good morning.
Sir, within a couple of minutes, we are going to start.
Sure.
Only 1 or 2 minutes, sir.
Okay, fine. Absolutely no issues.
So now we are going to start the inauguration session. All the participants are requested to please keep your mic in mute mode. Honorable Professor Binod Kumar Kanojia ji, Director, NIT Jalandhar. Professor S.K. Prashad, Honorary Scientist, CENS Bangalore. Deans, Registrar Sir, Dr. H.K. Mishra ji, Professor Avinder Singh, Head of the Department of Physics, Coordinator of the course, Dr. Ashish Raman, Dr. R.R. Sinha, Dr. Aditya Prakash, faculty members, my dear colleagues, and their participants. A very good morning to all of you. On behalf of Physics Department, Mathematics, Humanities and Management, it's my privilege to welcome to all of you in 5-day online short-term course on emerging trends and modeling in advanced functional materials and devices. We are sincerely grateful to keynote speaker Professor S.K. Prasad ji for kindly accepting our request and gracing the inauguration function. With the aim of imparting knowledge to young minds, Director Sir has always motivated us to organize academic activities which are directly beneficial to the society in the diverse area. We thank Director Sir for his vision, continuous encouragement, inspiring mentorship, time-to-time guidance, and all kind of administrative supports. Director Sir has always provided an opportunity to the faculty of the NIT Jalandhar to explore the research activity not only at the departmental level but also in the diversifying the origin collaborating at the interdepartmental level. We are also grateful to Dr. H.K. Mishra ji, Registrar, for his keen interest in this STC and wholehearted support. This 5-day STC program will focus on synthesis, characterization, design, development of functional materials, physical aspect of soft functional materials like liquid crystals, nanomaterials, self-assembled materials, solar cells, thin films, semiconductor devices, composite for biosensors, etc. Due to their technological importance and potential application, these materials are extensively useful in all fields of science and technology. In this 5-day STC, we have raised 9 expert talks, and most of the eminent experts are from IITs, NITs, R&D centers, and research lab. We are thankful to all the experts for accepting our request and sparing their valuable time to enhance the knowledge of the young minds. Nearly 200 participants have registered for the course, and I'm sure this online STC will be highly beneficial to the academician, R&D persons, scholars who are concerned to explore such materials and their potential applications. Once again, I welcome you all. Thank you very much. Now I request to our head of the department, Professor Arvinder Singh ji, to kindly address the participant. Over to Arvinder sir.
Yes, good morning to all the participants. First of all, I am thankful to the body director, Professor Vinod Kumar Kanojia of our institute, for motivating the faculty for organizing this course. I highly appreciate the efforts put in by the convener and the coordinators, Dr. Parveen Malik, Dr. Ashish Raman, Dr. R.R. Sinha, and Dr. Aditya Prakash for organizing this short-term course on emerging trends and modeling in advanced functional materials and devices. As you all know, functional materials are widely used in various fields because of their excellent properties. They are designed and synthesized for some specific functions. Functional materials are being used for the development of several high-end technologies and will definitely play a key role for the development of future technologies. Dear participants, during this course, you will get a chance to interact with the eminent scholars from various reputed institutes of India. I'm sure you will gain a lot from their expertise, and this knowledge will be beneficial for you for your research works. I'm sure you will all enjoy deliberations of this course. I am also thankful to Professor Prasad for accepting our request for the keynote lecture today. So with these words, I wish all the best to all the participants. Thank you.
Thank you, Arvinder sir, for the nice words. Now I request the coordinator of the program, Dr. Aditya Prakash ji, for give a vote of thanks.
Thank you, sir. At the onset, I, on behalf of the organizing committee of the STC on emerging trends in modeling and advanced functional materials and devices, express in beneficial for the participants have diverse learning experience. We also that participants don't but also themselves the required competence. Participants for your presence and positive response in registering for the STC on emerging trends and modeling advanced functional materials and devices. I'll present gratitude to the organizing team members and colleagues, Dr. Ashish, Dr. Arachna, winners of them. STC may not have been possible. Once again, I'd like to thank all our participants for their curiosity and online presence today. I thank you all. Thank you. To Dr. Praveen Malik.
Thank you, Dr. Aditya Prakash. Now I request to, now we are going to start our technical session, and let us welcome Professor Krishna Prasad ji for this keynote talk. So let me introduce, and I think in the field of material science, condensed matter physics, there is no need to give such kind of the introduction because he's a well-known figure, not only in India, but the worldwide. But at a protocol, I have to, that's my duty to introduce the other participants also. So on behalf of this, as a coordinator of this program, let me thank first of all Professor Krishna Prasad ji for this nice opportunity, and I'm very thankful to you, sir, that you have accepted this my request and accept to be the keynote speaker of this 5-day program. Thank you very much, sir. So Professor Krishna Prasad obtained his PhD degree from the RRI Bangalore after a brief stint as a visiting scientist at the Technical University of Berlin, Germany. He was appointed as a scientist first at the RRI, that is Raman Institute, and later at the Center for the Liquid Crystal Research, Bangalore. Currently, Professor Prasad is visiting at the Center for the Nano and Soft Matter Sciences, Bangalore, as an honorary scientist. It is a great pleasure for the members of the liquid crystals. Professor Krishna Prasad work is focused on several frontline areas of the liquid crystal materials, with at the forefront of soft condensed matter from both basic and technological aspect of view. At this center, he has developed and nurtured a dedicated band of scientists working on both the physical and chemical aspect of liquid crystal science, which has achieved several breakthroughs in this field. Currently, his interests are nanosoft composites, photoluminescence, photostimulated phase transitions, the influence of restricted geometry, soft robotics, and application-oriented research. He has authored more than 300 research papers, which are published in international journals of 5 perfecta and well received, and 10 patents to his credit. He has also guided several students for PhD degree, besides postdoctoral research experience in various organizations abroad, including the Devil Research Laboratory, Washington, DC, Hungarian Academy of Sciences, Budapest, Bulgarian Academy of Sciences, Sofia. He was ITI Research Manager at the National Institute of Materials and Chemical Research, Japan. Professor Krishna Prasad is also a recipient of the prestigious Japan Society for Promotion of Science JSPS Fellowship, C.V. Raman Scientist Award from the Government of Karnataka, and a Fellow of the Karnataka Science and Technology Academy. So once again, thank you very much, sir, for accepting our request. Over to Professor Krishna Prasad.
Am I audible?
Yes, sir, you are audible.
Very good morning. Very good morning to all of you, and especially to the director, Dr. Praveen Malik, Dr. Arvinder Singh, and the other dignitaries present, as well as all the participants of this short-term course, which will run over 4 days, 4 or 5 days perhaps. It's a pleasure to be here, and I'm extremely thankful to Dr. Praveen Malik for giving me this opportunity to have this keynote address. It would have been a pleasure to be there in Jalandhar in person, and I always enjoyed traveling around Punjab And I think the last visit that we had was, I see Pankaj Kumar over there, the Chitkara University. What a nice hospitality we had is what we keep talking about. And it so happens that after that, we have never had a in-person kind of liquid crystal conference, which we are craving for. Perhaps this year, we should be able to meet in person and talk to all the colleagues and enjoy the technical deliberations, especially of such conferences. With that little thing, I would like to start my presentation. I don't think you're seeing my screen, is it? I said present and then I switched over to my presentation, but I still don't see it there.
Yes, sir. Not yet.
Any particular reason? Because I'm not the presenter here. Should I re-log in as a presenter and then come back?
Yes, sir.
Okay.
Sir, who is the host of the meeting?
Myself.
Sir, I think you can make him presenter. Please check.
Dr. Aditya, Dr. Ashish Raman, sorry, Dr. Abhinav.
Yes, sir.
Can you call me at 3208?
Yes, sir. Yes, sir.
Malik sir, you can make as a host to sir, and sir can share the PPT. You just go to the name of the Prasad sir, and then you can make him as a host. Sir, you are on mute mode, sir. Krishna Prasad sir, आप mute हैं sir अभी, please. You are on mute.
Sorry. Yeah. No, I again logged in, but it doesn't allow me to present my PPT.
So Dr. Parveen Malik is looking into it. And,
Okay.
you will join.
Yeah, I'll just wait for it.
Dr. Prashad,
Yes.
I have made you as a co-host.
Okay. So should I log out and then come in again?
You can try again.
Okay. I will. No. It's not allowing.
Sir, is there any option means for
Yeah, it should
sharing
have-
the screen? Sir,
It should have shown me a screen wherein it says share, but I don't see that at all. I'm going to the full screen.
sir, kindly go to the present now.
तीन dots
Okay.
दिख रहे आ रहे हैं। दोनों में post होना है।
Hello?
Yes, sir.
Yes, sir. Yes.
It gives me the companion mode. It doesn't give me the regular share screen.
Dr. Raman, can you suggest?
Sir, I think there is an option below that present now. So you please click on that.
No, the present is grayed out now. So therefore, the only thing it does is it takes me to the companion mode. It doesn't take me to the standard share screen.
Okay.
So unless you allow me to share the screen, it won't.
ओके इधर तो ऑप्शन आ रहा है मेरे पास में सर मलिक सर फिर एक काम कीजिए आप ना अपने उससे शेयर कर दीजिए स्क्रीन सर की जो पीपीटी है और सर जैसे बताते हैं उसके अकॉर्डिंग चेंज कर दीजिए अगर ऑप्शन नहीं आ रहा तो
I'm trying to rejoin again.
Okay.
I'm using 2 logins. Would that be a problem?
Yes, sir. I think that is the problem.
Okay, then I'll log out of the second one and then let's see what happens.
Yeah, I will
Okay, sir.
suggest that you log out from both of them and just log in from one screen. I think that will be helpful.
No.
Malik sir, please check whether Krishna sir is the co-host right now or not. Please check, Malik sir.
Yes, sir, doing it.
Prasad sir, can you see your entire screen, a window, a tab in present now after going to present now?
I'm only seeing the participant video kind of thing. I don't see what happens typically, as far as my experience goes, is you get a little window which says share.
Okay, sir.
Okay, so on clicking that, it will take me to any application that I want to share the screen.
Ji, sir.
But this is not happening.
Okay, sir. Okay.
Sir, on the bottom of your screen, is there any window?
None.
Means
I
where the
have the
leave call is
Sorry?
there. Means I think leave call is there, and then present now.
Okay, I leave the call. Just leave the call.
There is a button for the leave call, and then
Yeah. So
Present now.
next to that, for example, there are options available.
yeah, then
And
present
I
now. Sir.
say full screen, for example. It takes me, making the full screen. It's like typical video full screen.
No, sir. Please, sir, don't click on that.
Okay.
That. Full
What should I
screen
do?
Means that leave call. Then 3 dots are there. Then present now option is there.
There is no present option there. Yeah, of course, I do know that an upward arrow means the presentation kind of thing. I have already clicked that.
Okay, okay. So I will show you on my screen.
Yeah, please go ahead.
Sir, is it visible?
Yes, I do see your screen.
Sir, here you are having.
Yes, sir, that's exactly what I'm talking about. It is grayed out right now. It's gray, so I can't click on that.
Okay.
Sir, Ashish sir, is sir the co-host or not?
सर मेरे पे इधर नजर नहीं आ रहा.
Malik sir, I think he can only inform.
Yeah.
No, Prasad sir is now host. I can see. I checked it.
One more time, I could probably log out and come in again. Rejoin the meeting.
Yes, sir. I think you can try that, and the other.
No, I'm requesting Dr. Raman, if
Yeah,
I'm
yeah.
pronouncing your name right.
Yeah.
Should I dare say join now or present?
Where, sir?
In the rejoin login window,
Yeah.
should I say rejoin or should I say
Sir, first
present?
you please leave the call and then.
Yeah, I'll do that. But if I leave the call, I won't be able to talk to you. So therefore, I'm checking with you now.
Yes, sir. I think it will be best if you just close the window and then click onto the link again and then try to rejoin. Hopefully that will help.
No, you are not getting the point. I am saying when I log in, should I say just rejoin or should I say present?
So I think rejoin is the option.
Region will be better option.
I'll
Region
try
will
both
be better
perhaps.
option.
I'll try both. I'll just leave the call now.
Okay, sir. Okay.
Okay, you do see me now. I'm clicking the present now.
Okay.
So I'm saying your entire screen. See, by now I should get a window which says a little window
Yes,
which
sir.
shows me the
Yeah, please
same.
click on that window. Please
Yes,
click on that
but I
window.
don't see it.
Okay.
And maybe you can go to present.
So try Alt Tab
Alt tab.
whether the window reappears.
Hold on for a minute. No, I don't think so. I'll probably. Do you see my PowerPoint now?
No, sir.
No, obviously that is not the solution then. So I'll just see again an Alt tab. Now it takes me to another application, that's all, but it doesn't share the screen. Goodness gracious. This is truly Murphy's Law. But the presentation is so big, I couldn't have emailed you. Otherwise, I could have asked someone to run it for me.
Sir, if you don't mind, you can send the PPT to me and I will run it from here.
Exactly, that's what I thought, but it is 50 MB.
Yes, not
50 MB.
50 MB.
So you can load
Put
it
it on the
Google
drive. Put it on the drive.
Yeah, put it on the drive.
Okay.
Just send the link to the Praveen
Okay,
sir and he'll
I'll do that. I'll do that. Just for a second. I'm not getting the present kind of thing.
We request the participants to be kindly patient enough. We'll soon be resuming.
Hello. Hello.
Yes, sir.
Am I audible?
Yes, sir. You are audible.
Can you see my screen now?
Yes, sir. We can see.
But something else. Yeah.
Hello. And
Yeah.
sir,
Can you see my screen now?
yeah, can you see the slide, sir?
I'm trying to do it from this end itself.
Okay, sir. Okay.
Hopefully that's the control that I have. Check whether the slide moves to the next one, then I will know whether things are working all right or not. Did it go to the next slide?
Yes, sir. It's working now.
What do you see on my screen?
This is outline, sir. Outline.
Excellent, excellent. Thank you very much, and I'm extremely sorry. I took the suggestion of one of your colleagues to say that I should use another browser. I was using Chrome, and I switched to Firefox, and it seems to be working for whatever reason.
Okay,
I'm very
sir.
sorry for the delay. It's a pleasure again to thank Dr. Praveen Malik for inviting me to give this keynote address on anisotropic soft matter confined in meso or nano networks. In this emerging trends and modeling in advanced functional materials and devices short-term course. I will not be talking much about modeling, but rather on the material aspects of one particular kind of soft material. That's the kind of intention that I have. Here is the outline to my talk. And I'll be beginning a very brief introduction. We have already lost about half an hour owing to some issues here. So after that, I will start with introducing different kinds of networks. And first one that I want to do is something called a thixotropic network, which is actually a network formed by colloidal particles. And in this, what we found, the important result that we found was that the network of these insulating nanoparticles enhances the electrical conductivity of the system. And then we are going to talk. About the electrical switchable smart windows, which actually bring in the effect of carbon nanostructure reinforced networks. And then I'm going to look at, if possible, biopolymer network. The next topic, which actually I'm going to spend a significant amount of time, is the anisotropic photoluminescence, something that's special that comes only from liquocrystals. And the ultimate goal in this regard is to have a freestanding electrically switchable emissive sheet, and also to bring in new kinds of display, liquocrystal displays, which are emissive, which liquocrystals otherwise are not. And then the last topic that I have selected is photomechanics. I chose this for two reasons. One is that this is one of our latest activities combining light and mechanics, and also because the person who worked on this a lot, Dita Jayoti, comes from your NIT. She's a product of NIT Jalandhar. She got her PhD degree from there. So therefore, I added this part wherein we are going to look at twist sense control using hybrid aligned LC elastomers. So let's begin with a very brief introduction to soft matter and especially to liquocrystals. These few slides I've put in for the simple reason that this conference, this course seems to be addressing people from multiple disciplines. And so therefore, I wanted to give a glimpse of what soft matter and liquocrystals are. So the first one that we should look at is why call a soft matter at all? And the definition that goes today is from this Nobel laureate, P.G. Dijeune. He said one simple statement during his Nobel talk: all physical-chemical systems that have large response functions should be referred to as soft matter. Or, to put it in colloquial terms, you can say mild external influence has a very big effect. Or if you want to go into the depth of how soft matters are defined, let me put the first and the second point here. Substances whose molecules can be made to move significant distances. Let me get the pointer. Significant distances by the application of comparatively weak forces. Or if I want to talk in terms of the energetics of the system, these systems are held together by non-covalent interactions, and so therefore they are weak interactions and often guided by energies of the order of kT, K being the Boltzmann constant, and thus they are comparable to entropic forces. And so therefore, playing with them, making them change their structure or making them change their functionality is not all that difficult compared to the typical hard materials that one talks about when we are talking about typical semiconductors or metals, for example. So it is this energy scale which makes them more comfortable to work at room temperature itself. And so therefore, one important aspect is the quantum aspects could be generally unimportant unless you probably bring in very specifically the quantum effects, which we are going to see in one particular topic. So generally they do self-organize into mesoscopic physical structures that are much larger than the microscopic scale of atoms and molecules, but of course they are much smaller than the overall scale of the material. So therefore they fit into the mesoscopic scales. Or the players in the soft matter category, several of them that we come across in our daily life too. These could be polymers, these could be surfactants and emulsions, colloids, granular materials, gels, proteins and DNA, and of course liquid crystals, a topic that I'm going to stress upon today. So let's begin with a 1 or 2 slide introduction of what liquid crystals are. And I apologize to people who are here, who are experts in the field of liquid crystals, including Dr. Praveen Malik and Dr. Pankaj Kumar and others from the liquid crystal community. So bear with me for a couple of slides. So liquid crystals actually, as the name itself suggests, comes from 2 different categories. One, the properties come from the liquids, and the properties come from crystal side as well. So it is like putting together the properties of 2 different systems that you come across when a system melts from its solid or a crystal phase to its final journey of becoming a liquid. So a solid made up of molecules which are not spherical but rather lap-like or rod-like kind of shape. They do have a 3-dimensional periodicity, and that's well confirmed by, for example, X-ray diffraction. You get Bravais reflections coming from such solids forming the crystalline state. The ultimate state, of course, is the liquid state, wherein there is no positional order itself. But in addition to that, you should also see, this is something that we are very familiar with spherical molecules also, and there is no positional order in the liquid. But since they are rod-like shape, you should also consider an additional property that along with the positional order, the crystal will also have an orientational order, by which I mean that the rods, if I'm considering these entities as the rods, all the rods are oriented along one particular direction. This is what is referred to as the orientational order. That order is completely lost if you go to the standard liquid phase. So thus one should probably think that there could be in intermediate phases. And I said could be instead of should be, because although this kind of a 2-step melting can occur in systems, there need not be that kind of a two-step melting, and the solid can directly go over to a liquid. So only in certain specific cases, such intermediate liquid crystalline states are seen, and one such liquid crystalline state I have shown here, which is referred to as the nematic liquid crystal. What needs to be emphasized here is that the nematic liquid crystals, the rods are more or less pointed along the same direction, but they do not have any kind of positional order in any of the three dimensions. The orientational order is signified by this arrow that I have shown. It's a vector which is headless, which means the up and down directions are one and the same for the so-called director, which signifies this particular arrow direction. So if I want to quickly see this kind of a comparison, the solid has both positional and orientational order. The liquid has neither positional order nor orientational order, wherein in the simplest of the liquid crystals that I have shown here, which is what I'm going to use in the entire stream of my talk, is going to be one particular liquid crystal referred to as a pneumatic liquid crystal that does not have any positional order along any three directions, but it has orientational order. So you can call it an orientationally ordered fluid. The molecules which form these kinds of things come in at least three different shapes. The only important aspect to those molecules is they should not have any shape isotropy, which means that their dimensions should be different along different directions. For example, if it's a rod, the length of the rod is different from its diameter. If it's the disc, the thickness of the disc is different compared to the diameter of the disc. Or if you have a distorted rod, you can call them as banana-shaped or bent-core kind of liquid crystals. So these are the entities which form the liquid crystals. And you can also add chirality to this. I'll come to the definition of chirality. I'm only introducing one simple aspect here, which talks about there is an additional order which you can gain by having a handedness to the kind of molecules. The molecule is kind of chiral. To give you two examples of what chiral molecules could be, one could be sugar, the other could be DNA. They are not achiral systems, but rather chiral systems. So since I'm talking about confining these systems in meso or nanoporous networks, I should be asking the question of why I should confine these materials. The molecules confined in narrow pores exhibit a wide range of physical behavior, and the wall forces, the forces from the confining walls and the competition between fluid wall and fluid forces could cause several things to happen. But the topics of interest to us are phase transitions, especially when we are confining them into liquid crystal, in matrices. And so therefore, I'm looking at phase transitions as examples here. And so confinement-induced fluid transitions have been reported for quite some time now, even as recent as the last year. Coexistence of multi-layered phases, especially water when it gets confined, shows many interesting properties, and they have been studied for quite some time again. And the importance of flexible confining surfaces has been looked in this particular article that I have cited here. Localized phase transitions in single neuron cells, so it can encompass biology as well when we are talking about confinement and phase transitions, and several other examples that I have quoted here. All these make confining geometries very important. The features that are best specific to liquid crystals when they get confined is the aspect that liquid crystals exhibit degrees of order which are more compared to the very simple one that I showed as the simplest of the phases, namely the pneumatic liquid crystals, which has only orientational order. You can bring in step-by-step build-up of the order as the system approaches towards a crystalline phase. And the transitions are second order or at best weakly first order, and so therefore playing with this system we can understand the universal aspects of phase transitions of a variety of systems, and these are typical representatives of soft materials because they are elastically weak. I'm going to touch upon that point. And the complexity of the effects or because of the competition between elastic, surface and external field forces like the electric or the magnetic fields. I'm sorry. And we should also be considering smooth versus rough surfaces, especially at local levels. And most important, when I'm bringing in liquid crystal, is the anisotropy. And we already saw something about anisotropy in terms of shape anisotropy. I'll spend a minute or two on the anisotropy in physical properties. The shape anisotropy that we talked about is that of the molecules themselves. that they have different dimensions along different axes. But here when they assemble into a leucocrystal, that kind of a shape of anisotropy translates into the physical properties as well. And a couple of them I have listed out here. One is the optical anisotropy, also known as the birefringence or double refraction, something that you may be familiar because of the courses that you would have gone through. This is simply nothing but the birefringence is given by the difference between the extraordinary and the ordinary refractive index of light, and that's finite in liquid crystals. And dielectric anisotropy, a similar kind of thing, but the frequency is much lower than the optical frequency. And so therefore, you would be talking about epsilon parallel, which is parallel to the director direction or the orientational direction of the matic. And that dielectric constant is perpendicular to the director direction. The difference between the two is finite, and so therefore we call these as dielectrically anisotropic systems. And there could also be elastic anisotropy, at least of 3 primary different types, referred to as the splay, the twist, and the bend, depending on how you confine these systems between the containing surfaces. So you can define, for example, if one surface is stretched compared to the other one, then you will have a splay, opening up of the orientation direction of the molecule, splaying from one direction to the other, and twisting from one plate to another. There can be a twisting of the director and the bending of the director, which is obvious from the name given to itself. So the free energy of the system will depend on each of these elastic constants which govern such deformations, and one can arrive at how simple it is to deform these kinds of molecules, the energies involved being extremely small, or in terms of the forces involved, these are in the piconewtons. So therefore, even a small perturbation as putting a dust particle can deform these systems very easily. And as far as the kind of confining materials that are popular nowadays, I have listed out a few here. I won't go into the details of many of them, except to talk about only 2 of them, because I'm going to employ them in the kind of description that I'm going to do in the rest of the talk. So the first one is referred to as the aerosol. It's a commercial name, aerosol. It actually involves on the surface 2 or 3 different kinds of atoms: oxygen, silicon, and hydrogen. Obviously, OH kind of contributions coming into the picture. Talk about the hydrogen bonding that's available to the system, and the pore shape is like that of a void. You create a void in situ and have the material inside, and the pore bits, you can vary them over a very large length from an external point of view. And another kind of confining that I'm going to look at today is have them inside a polymeric network. And so therefore here I could be talking about droplets or voids or between fibers. These 3 kinds of combinations can make up the confinement in these kinds of materials, or the confining network. And the pore bit again is largely variable, controlling the amount of polymer that you have in the system. So the first one that I'm going to talk about is the thixotropic network. To those who are not familiar with what is thixotropy, I'm just giving a half a slide kind of introduction here. Thixotropy is the property of certain fluids and gels. Fluids, we are already talking about fluids in terms of leucocrystals. So that's the interest here in thixotropic systems. Fluids and gels are becoming thinner when a constant force is applied, and after reduction of the force, the viscosity recovers fully to the initial state in an appropriate period of time. It is not an instantaneous one. It takes its own sweet time to do that. Thixotropy is a time-dependent phenomena, as the viscosity of the substance must recover after a certain period of time when the applied force is removed. This need not be very isotopic kind of systems. You are already familiar with the thixotropic systems, and one simple example for that is the ketchup. When you are trying to pour the ketchup out of the bottle, you need to tap the bottom of the bottle to make the ketchup come down the mouth. But then once it starts flowing, it is like a liquid. Again, when it settles down on surfaces, for example, on French fries kind of thing, again, it becomes a solid. So depending on the amount of shear that you are putting on the system, the viscosity of the system changes right from that of a liquid to that of a solid. So you can construct such thixotropic networks using a very simple architecture that comes from particles which are commercially sold as aerosols. And these aerosol particles are siloil particles having, for example, SiOH kind of surfaces. And it is the presence of OH on the surfaces. So two different particles, I have put two different particles here in the proximity of each other. The OH can form a hydrogen bonding depending on the proximity of the two particles. And this gives rise to, for example, aggregates of the particle. Particles can come together in a few number, or they can form agglomerated aggregates, or finally, or they can form a 3D network altogether. So it is the void that I was talking about. It's created by these 3D kinds of networks. And now if you apply a shear, the 3D network will go back to an agglomerated aggregate, or if you allow it to rest, it will come back to the 3D network. For example, I have put here an aromatic liquid crystal confined in such a void made up of aerosol particles. So if I use such particles and put them in a liquid crystal, there is a gel that is formed, a thixotropic gel that would have been formed. And you see, what you see here is the microscopy, polarizing microscopy picture taken in the thixotropic network of the system. Lo and behold, to those especially from the liquid crystal background, this appears like any other ordinary pneumatic without giving you much hint about the containing porous network that is present because of the thixotropic system that the aerosol have formed. Now, if you try to do, if you conduct electrical conductivity measurements by incorporating a conducting particle such as, for example, a gold nanoparticle into the system, drop a few gold nanoparticles into the system, and then what you see in the pneumatic, you have some dark regions which arise because of the presence of the gold nanoparticles. If you measure the conductivity of such a system, they show a percolation behavior, which means that at very low concentrations, for example, the conductivity is that of a true insulator, which a liquid crystal is. Liquid crystals by design are made to be insulators because of the display industry especially. So, but when you go on adding gold nanoparticles, the conductivity could pick up by a few orders of magnitude in a very sharp rising curve. The magnitude of the conductivity increases, which can be described by a power law, which is a very standard description for a percolation behavior. So now the interest in this kind of a thing was to confine it in a thixotropic network, and what will happen to the conductivity of the system dominated by the gold nanoparticles. Because our expectation was, since you are going to put insulating particles, aerosols are insulating particles, and since you are going to put insulating particles into the system, you are anticipating the conductivity to drop in these kinds of phases. But to our surprise, it was to the contrary. What I have shown here are the temperature-dependent conductivity measurements in three different systems. One is a liquid crystal, which is behaving like a Paka insulator. Please note that the conductivity is given in terms of the microsiemens per meter. And so therefore, you see a very small value of the conductivity, which again decreases as you lower the temperature. It should happen because of the Arrhenius forces which are behind the conductivity in these systems. But you add gold nanoparticles to such a system, there is a significant increase, which we already saw is because the percolation behavior. But the temperature dependency is again parallel to that. But now when you add the insulating particle, which is the black set of data here, what you see is a further enhancement in the conductivity, which is anathema, considering that the siloil particles are insulating particles. We are putting additional insulating particles into the system. So therefore, we should anticipate the conductivity to drop and not increase. But what we see here is an increase in the conductivity by nearly a tenfold value. So therefore, we analyze these kinds of things in terms of what could happen in terms of the architecture in the medium. And what we see is the blue ellipses are the liquid crystals, the yellow globules are the gold nanoparticles. And what you have are, for example, in these situations, you have an insulating network which gets formed, which are the black lines here, over and above that of the gold nanoparticles. And because of this thixotropic network that forms, the gold nanoparticles are frozen in space because pneumatic is a liquid, and so therefore thermal fluctuations play a large role in them. So the contact between the gold nanoparticles is not constant with time, but when you impose the thixotropic network, that action is frozen to a large extent, at least wherever the thixotropic network exists, and so therefore you are not allowing the system to have thermal fluctuations wherever the gold nanoparticles are present, and therefore we call this as patching up or the healing of dead bonds. And therefore the mean free path, if you talk in terms of the solid state physics, the mean free path in the system increases, and so therefore you end up with a better conductivity in the system. I won't go into the details of this, and probably I'll skip this topic because of lack of time. You can do a similar kind of thing with molecular-based hydrogen bonding systems as well, and you can increase the conductivity by significant orders of magnitude, and then also change the temperature dependence, going from a truly arrhenius, which should be true for liquids, but to a ballistic kind of electron transport that is characteristic of hard systems and not soft systems. I won't go into the details of that. I'll now switch over to the second topic that I have mentioned, electrically switchable smart windows. And here I want to look at very quickly the progression of displays. Long ago, the only way that you could disseminate information was through newspapers. And then, of course, we had the televisions. But the televisions, when we had at our homes, when we were young, and that was not too far ago, although I'm already an old timer now, people calling me an honorary scientist. So therefore, these televisions, which were made using the CRTs or cathode ray tubes, were pretty voluminous, and therefore they were heavy also. Some of you may be able to recall that these televisions used to weigh something like 50-60 kgs when we had something like 40 inches of television. But then the advent of liquid crystals and for the development of the display devices brought in the flat panel displays, like the computer screens that you have, or the laptop screens, or the kind of televisions that you have today at home. These are the flat panel displays. But the drawback of this is already seen, but people are comparing the voluminous televisions with, for example, the CRT televisions with a sumo wrestler, and probably the flat panel television should be compared with somebody who is soft and fine kind of thing. But people are not satisfied with the thin, rigid panels that one is talking about in terms of the display device that we have. So people are talking about moving away from rigid display devices, going to a bendable, lab-level demonstrations were held in the years that I have mentioned. 2010, we had by 2010 we had already come to the completion of rigid systems. By 2015, people were talking about bendable displays. In the 2020s and beyond, we are talking about foldable and rollable kind of devices. And we are now talking about rollable displays, which can be, or the flexible display architectures, is probably can become commercial few years down the line. And the advantages of flexible display I don't have to be highlighting here, except to mention that still rugged, they're lightweight, they're very thin, ability to curve, flex, roll, fold. Portability is an important thing. I can, for example, take the laptop screen, get it under my armpit, and then take it to the class, hang it on the wall, and then start my presentation. That kind of an idea is what people are talking about. Low power again, and non-breakable, that's a big advantage. You can't drop, even if you drop your mobile, you won't be too much worried, unlike what happens today with the kind of rigid devices that we have. Plethora of applications, plenty of them. I don't have to be going through all the applications. Wearables is an important aspect that we are going to talk about. Of course, the weight is also going to significantly reduce. We have already brought down the weight from about 60 kgs to 60 grams, 600 grams, and probably in bendable devices 60 grams, and in rollable probably comparable to that kind of a number, with the thickness of the device being reduced to something like about less than an mm kind of thickness of the display device itself we are talking about. But the present day displays actually suffer one serious drawback. they employ birefringence, and so therefore viewing angle can be highly restricted unless you pay a significant amount of the money to the device. For example, it is like buying an iPhone vis-a-vis a low-cost mobile. iPhone costs so much because they employ something called an switchable device, and the kind of yields in such systems are quite low, and that pushes up the cost of the system itself. And so therefore, instead of having birefringence, can we look at some other optical property in the material and then come up with the display devices which can probably have a far higher viewing angle so that people can sit around a television and watch it with comfort. That's the kind of idea that one has while developing these devices, electrically switchable transparency devices, which we call as fog on demand. The reason we bring in fog is for a very simple reason. Fog, the winter fog that we are talking about, and Jalandhar is a good place to talk about fog. And fog happens because of two kinds of materials that are present in the atmosphere: the water droplets and the air. The refractive indices of the two materials are different, as we all know, 1.3 and 1 for air. And because of this difference in refractive indices and the right kind of size of water droplets makes light to scatter significantly, which is what we call as fog. So now, as the sun rises, or as the system, as the environment gets heated up a bit, the water vapor gets evaporated. Since it becomes of a single refractive index, it becomes a transparent system, the fog gets clear. Can you apply the same to come up with a display device is the kind of thinking in these kinds of technologies. So what is happening here, and a couple of professionals who are in this audience, including both Praveen Malik and Rakesh Kumar, they work on this kind of system referred to as the PDLC, or polymer dispersed leucocrystals. So what happens in such systems is that you have a polymer C, or a matrix of the polymer, into which you combine leucocrystal droplets. The little circles that I am showing here are the droplets of the leucocrystals, with the molecules of leucocrystals shown as the rod-like systems. And now the droplets have the leucocrystalline molecules pointed in all possible directions. And the criteria to come up with such a display is that you have three refractive indices now. One coming from the polymer, it is referred to as the N sub P, and there are two refractive indices coming from the leucocrystal, which we are already familiar with: the extraordinary refractive index N sub E, and the ordinary refractive index, which is N sub O. And as we know for leucocrystals, I have already mentioned it, Ne is not equal to N naught. That characterizes the leucocrystal. But by design, it is made such that the ordinary refractive index of the leucocrystal is made comparable to the polymer refractive index. And obviously now you might have already started guessing how the system functions. So I have one, or the equilibrium state here. The blue patch around is a polymer which has the refractive index N sub P. The droplets inside have either Ne or N naught. Wherever it is N naught, of course, it coincides with the polymer refractive index. But because of the presence of Ne in most of the directions, Ne is not equal to Np. Since there are different refractive indices, any light that is put on the system gets significantly scattered. So the panel is a scattering panel. So now I apply an electric field to the system, and I've already talked about dielectric anisotropy. Because of the dielectric anisotropy, it couples to the electric field, a torque gets applied on the system, and the leucocrystal molecules want to reduce this torque. They do so by turning themselves towards the electric field. That's why all the rods now inside the droplets are pointing along the electric field direction, which is applied across this panel. So since they're oriented along the electric field direction, the light beam sees the ordinary refractive index of these materials. The ordinary refractive index is equal to the polymer refractive index, and so therefore N naught is equal to Np, and so therefore you end up with a transparent state. So we started with a scattering state, then the field was off. Apply an electric field, it becomes a transparent state, and the system can be very conveniently switched between the transparent and scattering states. And this can be created very simply by appealing to so-called spinodal or the binodal modes when you apply, when you mix two systems. If over certain concentration ranges, if they demix, then you create the spinodal or the binodal modes. And that's what is done here. The polymer and liquid crystal, they don't like each other generally. And so therefore, if you can somehow embed liquid crystals in the polymer architecture, then you have got this system wherein it is binodal, and at the same time, it creates the right kind of geometry, liquid crystals being confined in the polymer matrix, through which you can apply an electric field and make them switch between scattering and the transparent states. So owing to the kind of networks that can be formed, especially for certain concentration ranges, we call this as the Swiss cheese architecture. This is a typical image of Swiss cheese, wherein the emulsions of the fat are confined to certain regions compared to the matrix itself. So the kind of geometry that you get for the droplets which contain the liquid crystal and the surrounding polymer is similar to that of the Swiss cheese. We call this as Swiss cheese architecture. So if you have such a panel, so let's say this is the equilibrium state of the panel, and therefore it's a scattering panel that you have. I apply an electric field here. I have some text behind this panel. In the absence of the electric field, since the system is scattering, I cannot read the text behind it. But now I apply an electric field and I can see that it becomes transparent and I can read the text behind it. I can go back and forth switching this, and then I can control transparency or the scattering of the medium, and I can control also the grayscale, and by doing so I can create a display device by this simple architecture of a polymer confined network. And of course, a variety of applications. I won't go into the details of that for lack of time. Most important thing, apart from the esoteric aspects, wherein you can create a privacy in the office by having such a wall. For example, there is a wall here which you hardly see, but upon switching the electric field off, for example, it becomes an opaque screen, creating the privacy between the two enclosures across the screen. So apart from this esoteric or luxury aspect of it, you can also appeal to what is, sorry, I forgot to add the point here. You can create situations wherein the air conditioning load is going to be significantly reduced by having such scattering panels. What we talked about was a PDLC system or a polymer dispersed liquid crystal system, wherein actually the polymer content is significantly high. People typically talk about 60:40, 60 of the polymer and 40 of the liquid crystal by volume or weight. Densities are comparable in the systems. So therefore, you're talking about a large proportion of the polymer, and although it can be switched conveniently between scattering and the transparent states, the drawback of such polymer dispersed liquid crystals is the voltage that you need to apply to the system is pretty large. And because of these large voltages, even though the liquid crystals as well as the polymers are insulators, the power consumption by these devices is not insignificantly small. Apart from that, it also creates problems wherein the quantity of the polymer that you are going to have can become brittle over time, and this creates situations which are not conducive for commercial applications. So therefore, can we now look at the opposite situation of opposite part of the spectrum, wherein the liquid crystal forms a majority and the polymer is a minor component? That's what people have been studying as polymer stabilized systems. In these, the content of the polymer is only a few percent of the total of the system, and the liquid crystal dominates as far as the content of the system. So, but what people found early on is the PDLCs are mechanically rigid, whereas the liquid crystals alone, since it's a liquid, it is not a freestanding or a self-supporting system. But now can we combine the best of both the worlds? I still have the polymer, which is going to make it like a self-supporting system. The matrix supports the liquid crystal, and I still have the switching advantages of creating scattering in these systems, and so therefore appeal to the PDLC characteristics of having pure refractive index and not the birefringence of the native liquid crystal come into the picture. That's why people are working on polymer stabilized systems. Here, the minority, which is the polymer, can control the way the liquid crystal majority molecules operate in the systems. And so therefore, people have been looking at it from various aspects. And again, for lack of time, I thought I'll talk about some physics behind this kind of polymer stabilized system, but probably I'll skip this, except to show that you can create a variety of architectures, variety of polymer networks in these systems by purely controlling amount, finely tuned polymer concentrations in the system can significantly vary the kind of network you have, and you can do systems and you can do analysis like the fractal dimensional analysis, and then have a polymer concentration dependent fractal dimension entering into the picture. You can also bring in locally chiral systems, imposing globally chiral architectures by purely converting the local chirality coming from achiral molecules transferred onto the polymer fibers, which are going to freeze the chirality that is coming from the achiral molecules. So, but I'm sorry, I don't have much time to discuss the physics behind this today. So we did some modeling, etc. And therefore we could describe a non-intuitive kind of situations in these systems of how to control such networks and then appeal to the threshold fields in these systems. But probably what I'm going to spend a little time on is how we could actually reinforce these polymers. Why one had to worry about reinforcing the polymers? When I talked about the PDLC, because of the larger polymer content, the mechanical rigidity of the system is pretty large. But when you are talking about systems wherein the polymer concentration is low, then what you are going to see is the mechanical rigidity is seriously compromised because the low polymer content. So the idea was to see whether now you can somehow increase the rigidity of the polymer without increasing the concentration of the polymer. The standard kind of polymers that can get into a liquid crystal do not work at all. You cannot just change the chemical architecture of the polymer and then get these kinds of mechanical rigidities. So therefore, what we were borrowing the civil engineering kind of solution into this. Let's say we have concrete. The concrete becomes very sturdy because the iron rods put through the system. This is like reinforcing the concrete. That's why it's referred to as the RCC, reinforced concrete structures. And so therefore, we borrowed the civil engineering kind of solution. We thought that actually, can we incorporate some reinforcements into the polymer fibers? The first candidate for that purpose, we thought, is the carbon nanotubes. Carbon nanotubes, of course, as you know, Young's modulus of carbon nanotubes is extremely large. And they also have a shape anisotropy. So therefore, they appeal to the shape anisotropy of the liquid crystal on one hand, but at the same time, rigidity-wise, an extremely rigid system. Can we somehow get these CNTs into the polymer fibers? A lot of liquid crystal groups have been working on putting liquid crystals into CNTs into liquid crystals, and then looking at the property, structure property kind of systems. But the problem in putting into these kinds of architecture, on one hand, we want the CNT to be present in the system, but on the other hand, we do not want CNTs to be interacting much or in a direct fashion with liquid crystals. What is the reason? Main important reason is the CNTs have a large conductivity. And once you put a large conductivity into electrically switching devices, you are spoiling the entire show. Because once you make the system conducting, you're going to short the two substrates. And so therefore, no electric field can be applied. Or even if you apply, there's going to be a large double electrode kind of creation happening. And so therefore, the internal fields are going to be very small. And so therefore, you cannot allow the CNTs to be getting into the liquid crystal region, but select and go only to the polymer regions. And that we could do with a very interesting kind of single-walled carbon nanotubes, which are sheets with PMMA that was prepared by our collaborators in Central Leather Research Institute in Chennai. And we chose PMMA as the confining matrix, and by suitable chemistry that exists on the CNTs, now we could marry the CNTs and the base PMMA and confine the CNTs only into the polymer regions. And that resulted in an architecture very clear of that of a similar PDLC kind of system. I already showed the Swiss cheese architecture for a PDLC, and I also showed for the polymer stabilized system a fibrillar morphology. Again, I'm showing a similar kind of thing here. For PMMA, for example, you have a fibrillar morphology, whereas when you incorporate CNTs, you end up with a droplet morphology. Please recall, we had PDLCs which showed the droplet morphology, which is because of the rigidity of the system. So we could now get rigid systems, even though the polymer content was comparable to the typical PSLC system. So the CNTs were truly reinforcing the polymer network, and so therefore we were ending up with a droplet morphology. And we got several interesting results, and we also filed a patent which has been granted now. And Marlene Barral, who was working on this, was pretty happy with the kind of results that we got here. As an extension of this, PMMA is not something which people are happy about its biodegradability. And so therefore, Pragna, the student, was working on how to bring in biocompatibility to the system. And along with another postdoctoral person, Dr. Srividya, Pragna and Srividya worked together to come up with cellulose nanocrystals, which are now replacing the CNT to reinforce these systems. These cellulose nanocrystals were provided to us by a collaborator at IIT Roorkee. Professor Negi kindly provided these cellulose nanocrystals. You can't buy these cellulose nanocrystals and make them work with liquid crystals. So some kind of a special chemistry had to be found on these cellulose nanocrystals. And in fact, they were extracted from the groundnut shells. And so therefore, we also were talking about a waste converted into a useful product. And again, we applied for a patent to that. And Pragna is happy about that kind of an aspect. One main aspect of these kinds of systems wherein you are reinforcing the polymer network is the threshold voltage, the voltage which is the operating voltage for any liquid crystal devices. At such a voltage, there is a reorientation that takes place from one orientation to another. It is what gives you the bright and the dark states in a liquid crystal device. And that threshold voltage is a strong function of temperature because of the associated elastic constants involved. You go like the order parameter square, you have a strong dependence for such threshold. But when you reinforce these polymers, the kind of surfaces you create overcome all these influences from the elastic constant of the medium and keep the threshold voltage constant, more or less constant with respect to temperature, which is an important parameter because for a display device to work, you need to be attentive to the kind of threshold voltage that is needed to drive the system from one state to another. So given the temperature of the device, it could be easily varying between 30 and 45 degrees. Typical temperature variations, for example, in Delhi could be 30 to 45. And over these temperatures, the threshold voltage, operating voltage of the system changes significantly. It means the controlling electronic circuitry now has to account for this change in threshold voltage. And because of these kinds of changes, it becomes a complex problem to design device circuitry for the liquid crystals. But having such a temperature independent system, it is going to significantly reduce the circuitry for the system. So we have a plus as far as reduced threshold voltage, temperature dependent ones, simpler device circuitry, better grayscale capability, backflow avoided, faster switching systems, and mechanically rigid ones because the reinforcement. So there are a lot of advantages in having these reinforced kind of systems working as polymer stabilized liquid crystals. Again, I won't go into the details of that. Just to show two pictures of the device that we created. In the field of, you have a significant scattering, so therefore you don't see the text behind that. Whereas in the field on state, you see the text clearly seen because of the transparent state. I thought I will talk significantly about photoluminescence, but I see that I have about 20 minutes. Dr. Malik, you should please confirm. I have about 20 minutes.
Yes, sir, you can continue.
Okay. So I'll probably have a little bit of introduction to photoluminescence, show one or two aspects, and then go to the last topic of interest to the photomechanics. So the whole idea of photoluminescent systems, especially in leucocrystals, comes from this kind of a situation. When we see color, we just had Holi, so therefore I know that Jalandhar celebrates Holi in a big way. I have seen how Divya celebrates Holi, so therefore I can extrapolate that to the entire citizens of Jalandhar. So structural color or versus pigmental color is something that we are going to talk about. Holi that we talk about pigmental colors, a variety of colors, eye-pleasing colors are seen when you go to the market to buy for Holi. But one disadvantage of these pigmental colors, which are like dyes actually, is that they fade after some time. And also, some of these colors are very gaudy colors. As opposed to these colors coming from the pigments, you can talk about structural colors. Especially in the biological world, you see structural color a lot. For example, any bird, however long you want to look at a bird, for example, your eyes never get strained. You can't do the same thing about a heap of dyes. After some time, there is going to be a fatigue set in because of you looking at a particular color for a long time. And also, you have never seen the bird actually, the color of the bird actually fading away. This is because it's a structural color and not a pigmental one. There could also be angular dependencies for the color in structural colors, and a wide variety, and they are not gaudy. Other examples I have shown here, a peacock feather, for example, if you rotate the peacock color about the vertical axis, you will see that the color actually slightly changes as the angle changes. This is because of the confining structure whose periodicity is comparable to the visible wavelength that gives rise to the color. It is a diffraction. It is called as photonics as well. So because of this photonic character, because of the light diffraction property, you are going to end up with a back diffraction coming from such systems. And since it's a periodic one, the back diffraction is very efficient in this system and give you very pleasant, iridescent, bright colors coming from the system. So how do you bring in this kind of an aspect into leucocrystal? How do you bring in such color photonic structures into leucocrystal? It comes through a property known as the chirality, which I already mentioned in the introductory slides. So what is chirality? In pure English, it means handedness. So what is handedness? You know this very day-to-day kind of thing. When we put our right hand and put it in front of a mirror, you see as if we are putting up our left hand kind of thing. This is the right-left mirror that we are talking about. And this need not be through macroscopic objects like a hand, and therefore the handedness that we are talking about. This can extend to the molecular world also. And anybody who knows even a little bit about carbon chemistry can clearly tell you that a carbon having 4 different atoms attached to it does its 4-valent kind of property, then it becomes a chiral kind of molecule. The asymmetry present in the carbon is the reason behind the chirality you can bring into that kind of a structure. Therefore, there are chiral structures that we are all familiar with, at least in principle. This is like a DNA, for example. DNA has that kind of a chirality because of the kinds of molecules involved. And the chirality superimposes a helical structure into these kinds of molecules. Chirality can come where anywhere, civil engineering. And in addition, you can also have chiral objects, chiral organisms you can have. And here I have shown one such left and the right-handed kind of organisms that you can see in nature as well. Spiral staircases in civil engineering. And Indians don't want to leave the gods. We have the left and the right trunk Ganeshas. We call them as left Edamuri and Balamuri kind of Ganesha. The trunk is on the opposite sides. So the Edamuri Ganesha is actually a mirror reflection of the Balamuri Ganesha. So chirality plays a significant role in a variety of systems in our life. So how do you bring that to leucocrystals? I've already said that it's a chiral structure that I have. You take an ordinary magnet and put a few molecules of chiral carbon containing the chiral carbon atom, you can end up with a structure wherein I've already mentioned something about the director. The director is going to have, the director is going to have a spatial variation along a particular direction, and that direction will lead to a pitch of the molecules over which, after a certain distance, the director returns to the original direction. So this distance over which the director returns to the original direction after processing through the different directions is referred to as the pitch of the material. And if the pitch becomes comparable to the visible wavelength, you have diffraction taking place from such structures, and such structures are referred to as the photonic structures. The advantage, of course, is the pitch is tunable by a very different kind of parameters, including temperature. If you vary the temperature, you will change the pitch of the system. And if the pitch changes, the color that the system is going to reflect are also going to change. So I'll probably talk about the confinement in those systems and mention about the photoluminescent property. Here is something that we tried out. Putting systems in an achiral polymer and an achiral liquid crystal, you end up with the typical fibrillar morphology I've already talked about. I don't know, the contrast for the bottom one is very poor. I'm so sorry for that. Sorry, I don't see the slide is moving. Dr. Malik, I see that the slide is not moving on your screen. I have a parallel screen running here. I'm still stuck with the previous one for some reason. Could you kindly confirm whether you are seeing morphology as the title of the slide?
Sir, we can see morphology, and next is SCM and chiral.
Okay, very kind. Very good.
Next.
Okay, now I'll come to that. Okay. Because on my little screen, I see a previous slide. That's why I was just wondering. Okay, so let me continue, presuming that you are seeing the right slide. So the achiral systems, the fibers are striped fibers, wherein in the chiral ones, wherein you have a chiral component which transfers the chirality of the liquid crystal onto the fibers. You have a significantly curled up kind of polymer architecture. And so therefore, this chiral influence is what we talked about in detail when we were talking about these systems wherein the chiral transfer takes place from the liquid crystal to the polymer architecture. As you change the concentration, the amount of chirality transfer changes in a non-monotonic fashion. Up to a certain concentration, the system tolerates the transfer, and therefore you have more and more curling up as you increase the concentration of the polymer. But beyond a certain concentration, you lose the chirality transfer and they go back to striped fibers. I won't get into the details again, and I'll now come to the photonic properties or the absorption and emission properties of such systems. And so the only thing that we need to remember is deliberately we chose a very weak emitter into the system, and we saw that actually the system strongly absorbs, but its quantum efficiency is very low. The quantum efficiency is defined using an expression that is shown here, wherein there is a reference quantum efficiency material, and eta is the refractive index of the two materials, the standard and that of the parent system that we have. I is the integrated intensity under the emission peak, and A represents the absorption of two kinds of materials. And for reference, we chose rhodamine, which has a quantum efficiency of something like 70%. Compared to that, the kind of material that we have put in here, which is emissive, has a very low quantum efficiency of 0.1%. So probably let's skip this part, which is actually about chirality enhancing the emission. But now I come to the polymeric system, and even with achiral polymeric system, we saw that actually as you increase the concentration of the polymer, what you have is an enhancement in the emission itself. And this emission enhancement seems to be again non-monotonic, increasing up to about 3% of the polymer. But when it goes to about 6%, you see that it significantly reduces. This is true, and in a more accentuated way in the chiral system. Again, there is an increase from 0, which is this black curve that I have here. As you increase the polymer concentration, it increases, goes to a maximum to about 3%, and then when you increase it to 6%, the emission drops down significantly. And you can see this kind of a difference between the achiral and the chiral polymers. There is a significant enhancement in the emission coming from the system, purely because of the kind of architecture that we have when you have the chiral system propagating the polymer network. And at the same time, I have shown in a quantitative here that the emission level actually increases in a non-monotonic fashion, reaches a peak around 3% and then diminishes again. The analysis of these I don't have time to go through, but probably I'll switch over to something. You can also electrically switch these systems, and you see that when you have only the liquid crystal, there is hardly any change between the field on and the field off states. Whereas when you have only the polymer network coming in or the chiral material incorporated in the system, there is a little bit of change, or what we call as a photoluminescence anisotropy, the change between the electric field on and off states. But when you have both the chiral as well as the polymer architecture, you see that there is a large change between the field off and the field on state systems, and photoluminescence anisotropy is significantly large in this system and new in the field of soft matters, wherein you can control through the polymeric architecture as well as imposed chirality into the system, bringing anisotropy into photoluminescence. So probably I'll forget about the rest of the analysis here. We also created a three-state fluorescent memory device coming from such architecture, but sorry, I don't have time to talk about those things. This last piece before I go to photomechanics, which I am going to spend about 3-4 minutes, is on quantum dots as opposed to a dye which can get into the system, a liquid crystal dye or a liquid crystal discarding molecule which acts like a dye that can bring in the kind of changes that we saw. We also looked at quantum emitters or quantum dots coming into the picture and providing us emissive system, again anisotropy being the focus. In fact, Dr. Gautam Singh and his collaborators wrote a very nice piece on the existing knowledge of quantum dots and liquid crystals. In 2016, they wrote a report in Progress in Physics on this particular topic. But what they had been addressing is a quantum dot that comes from so-called 2-6 semiconductors, and the very popular combination being the CDS or the cadmium sulfide kind of quantum dots. But the problem is, because of the cadmium being a toxic kind of system, people don't like, and people are trying to move away from cadmium sulfide systems. And so therefore we started looking at other kinds of nanoparticles which actually are quantum emitters. And the one that we have seriously looked at is cesium lead bromide, which is actually a halide perovskite. I won't get into the details of this particular quantum dot, or actually what we call as a quantum cuboid because of the kind of architecture it has. And these quantum cuboids, when you put them in liquid crystals, they start organizing themselves into a linear chain, as you would see in the middle kind of transmission electron microscopy image. So they arrange themselves along their body diagonals and lead to some kind of a chain. Apparently, since you are talking about TEM, it appears to be happening only at a local level. But actually, when you view the cesium lead bromide incorporated into liquid crystals by doing a proper combination of the surface nature of the cesium lead bromide and the kind of liquid crystal that you need to have, you can actually start seeing chains of cesium lead bromide quantum cuboids lined up along a particular direction. So now in the liquid crystal architecture, along the direction, the quantum cuboids are going to organize themselves to be along the direction itself. So this image is taken with a polarizing microscopy, and to prove our points actually that these dark regions that you see are indeed quantum cuboids. We also took a fluorescent image of that, and that is clearly seen here. This is the polarizing optical microscopy without the fluorescent light, and this is with the fluorescent light, and you can see that actually these linear assemblies are coming from the quantum cuboids. Please let me emphasize again that the containing liquid crystal is a liquid actually for all practical purposes, and thermal fluctuations are a very serious problem here. And so therefore, if the linear assembly is still holding on, then the assembly of the quantum cuboids is very efficient, is what we are trying to show in this kind of a thing. And of course, you can see in fluorescence switching occurs in this medium. You have something called a double anisotropy. I don't have time to discuss that. And as I said, you can electrically switch these systems and change the fluorescence. Visibly, you can see the change switching between a very bright state to a very dull state going to the high field regime. So therefore, you can control the magnitude of the fluorescence change continuously in a grayscale kind of situation, going from a very bright to a very dull state. So therefore, you can in principle create display devices which are fluorescent, liquid crystal fluorescent devices. These are emissive displays because liquid crystals otherwise are passive devices, and they require a backlight to operate, and that leads to several drawbacks of the liquid crystals themselves. But these are systems which are emissive, and so therefore they could be considered a very potential candidate for future kind of liquid crystal devices. Probably I wanted to show a switching here, a movie, but probably I'll skip all those things and then go to just mention that the polymer network again can enhance the kind of photoluminescence anisotropy in the system. That's what I'm trying to show in these kinds of things. You have E7Q means you have the liquid crystal plastic quantum dots put into the system. Anisotropy is very low in these systems. You can enhance the anisotropy by confining it in a polymer network, what is seen here, and that is because of the efficient orientation of the quantum dots along the polymer chain itself. You can see that the polymer network is the background, and the bright dots that you see, which is also confirmed by the IDAX kind of measurement, you see that the quantum dots are very well oriented along the polymer direction, leading to high photoluminescence anisotropy in these systems. I'll skip that part and then go to the last topic that I want to mention about photomechanics. I want to take some 3-4 minutes, and then I'll conclude the talk. So what we are talking about is a stimuli responsive system, which means that responsive polymeric materials, they undergo size or shape change, which are triggered by stimuli such as it could be light, it could be heat, it could be humidity, electric or magnetic fields, or even the presence of volatile organic compounds or organic solvents. They are referred to as stimuli responsive systems. They're pretty attractive because several control parameters can be used for the purpose: the intensity, the wavelength, spatial and temporal polarization, tunability, or even non-contact operations. People are talking about even drug delivery systems using stimuli responsive systems. So applications could be actuators, sensors, artificial muscles, biomimetic robotics, etc. And the biomimetic robotics is what we are interested in, these kinds of systems. I'll probably skip this particular aspect that we initially started with when we talked about actuators coming from systems. We had actually used porous carbon nanoparticles, which are created from bio-waste and made by Dr. Hegde from the Christ University, but probably I won't discuss these details. But this laid the basis for our interest in photomechanics, and when Divya came to our lab, this was the stage at which we were in, and Pragya had completed these studies, and Divya took off from there, and that's why I'm mentioning these as our initial kind of system. So I'll skip this part and then go to. So the kind of actuation that we have is a near-infrared actuation. Near-infrared actuation, wherein we have the green strip that you see is our actuator, which is created by the soft systems that we have, which we have fabricated. It is clamped to a solid support, and of course, just to control the intensity, we have an ND filter. And so therefore, the NIR beam, the near-infrared laser beam, is going to fall on the actuator. That's the kind of simple design that we have. And when you actually impinge the laser onto these films, there's going to be a significant actuation, and that's why you see that actually the film gets significantly upon irradiation with the laser beam. This is the kind of architecture that we have. Of course, the rest of the architecture I'm not describing here. So several control parameters exist here. Porosity of the film that we have, its morphology, the Young's modulus, and the deflection magnitude itself can be controlled, and the response time itself is a tunable parameter that we are interested in getting good response times. What we found was that if you have such robotic systems, you can create not only a single direction actuation, but you can create a bidirectional actuation. I hope that this movie works. For example, this is how actuation takes place, and you see that actually, hopefully, yeah, you see that little strip actually going from its equilibrium state, which was vertical, and it has got actuated. And when the NIR is turned off, if you watch the tip of the film, actually it goes back to the equilibrium state. So this is the kind of NIR actuation that we are talking about for polymeric films. I'll probably skip this part, and we also created an IR-driven electrical switch for this. And so when Divya wanted to start on using liquid crystal kind of systems, the polymeric systems that we are talking about are the same base systems that we have with monomeric liquid crystals, except that now the mesogens could be forming a part of the polymer chain itself. And if you have cross linkers into these systems, they will give rise to the liquid crystal networks, which, depending on the kind of concentration or the kind of architecture that you have, you can end up with either a simple LC polymer networks, which will have a high TG, the glass transition temperature, with an associated kind of high elastic rigidity, or you can also create elastomers whose TG is very low and whose elasticity is also very low. So we were working on such systems, and Divya's idea was to have orientation of the liquid crystal polymers which are parallel to the substrate P side, and on the other side they are vertical to the substrate, and that's why they are referred to as the H side. And you have a continuous variation, a bend deformation going from the planar side to the homeotropic side. And having that kind of a thing, we did both experimental as well as modeling kind of investigations under the system. The modeling has been done by our collaborators at IIT Madras, where currently Divya is a faculty member there. And these simulations had several parameters which I have listed out here. And our interest was to model these systems considering that the rising temperature of the film depends on the light energy absorbed by the system, the local heat conduction, and the convective heat losses to the surroundings. So I'm going to show quickly a couple of slides here of the comparison between the experiments and simulations. The top are the freezes of the films, the actuating films that we have made of the liquid crystal polymers at different instants after the NIR is irradiated onto the system. And the same has been simulated with the kind of model that I showed. And lo and behold, we see that the simulations can effectively describe, even in a qualitative fashion, how actually the system gets energized, temperature rises, and gets actuated to different positions. So simulations actually copy the experiments so very well, showing us that the modeling has been quite effective. Quantitatively, we can show that actually, again, on the left you have the experiment, on the right you have the simulations. Again, both of them compare very well, and we have been able to achieve very large kind of displacements, something like 20-25 mm kind of actuations taking place in the medium. And actually the magnitude as well as the response of the system depends strongly on the thickness of the film, and that's what I have shown here. And response times can be counted in seconds in very thin films, and so therefore you could have a very good actuator coming from such NIR-driven kind of systems. For the details of the simulations, I won't get into the detail here. An additional thing that we call is something that I and Divya call them as the fluttering of the wings of the birds, and these were achieved by, for example, oscillations like that. And so therefore these are very effective system, fast relaxing system, large magnitude actuation system that could be very effectively used for actuators. This is my concluding slide. In fact, we have several potentials for such systems: self-assembled switchable photoluminescent displays, which I have talked about, PL modulated sensor, PL is photoluminescence, modulated sensors and switches, tunable analog memory device, one such device I just mentioned, smart switchable windows for energy saving and EMI shielding, liquid crystalline polymers as oxidic materials. I didn't have time to talk about oxidic properties. And something that we have as our final game plan is like switchable contact lenses, which I haven't even touched upon today. Just want to thank SERB, DST, and Tata Steel for funding, CNS for our current organization for nurturing our research, and a whole lot of people. In fact, I have mentioned only a few here. Several faculty at Center, Achal Kumar of IIT Guwahati, Jai Shankar of CLRI, Professor Negi of IIT Roorkee, and students and postdocs who were with us and who have been doing very well outside now. Pragya is about to get her degree. Marlene, who is right now in Spain. Divya in IIT Madras. Lakshmi Madhuri in Ben Gurion. Gurumurthy Hegde, who is a director of Christ University department. And KL Sandhya at MSRIT. And several others have contributed to the kind of work that I have presented today. And again, I would like to thank the organizers, Dr. Malik and all of the organizers who are putting together an excellent program which runs over 5 days and beautiful collection of programs. And again, thank the organizers for this kind of opportunity. I'm sorry I exceeded my time about 10 minutes. Very sorry for that. And thank you very much again. Thanks for all the attention.
Thank you, sir. Now we can take one or two queries from the participant side. For participant, if you have any query, then you can ask. Okay, if no other questions, sir, I want to ask one thing.
Please go ahead.
Sir, you show a transparency in a system like PDLC.
Yes.
So may I know what was the voltage at which you are getting the transparency, like from off state to on state?
Our main idea is not the PDLC, but rather in PSLC kind of systems. So therefore, with the PSLC, we can operate with only a few volts. 3 to 5 volts is all that we require to drive the system. And the emphasis that we were trying to do is, although you have all the properties of a PDLC, which requires typically 60 volts and above, these work at very low voltages.
Okay. Thank you, sir.
Thank you.
Well, last, let us thanks once again Professor Prasad sir for a wonderful talk and very informative talk. Thank you very much, sir. Thank you, sir.
Thank you.
Thank you very much. Thank you, sir.
Thank you. I'm going to sign off now.
Thank you, sir. Thank you, sir. Thank you so much.
Thank you,
It's
sir.
really wonderful talk.
Thank you.
Thank you, sir.
Thank you.
Now, let us invite the second speaker of this session, Dr. Akash Deep. Dr. Akash.
Yeah, good afternoon, Dr. Malik.
Good afternoon, sir.
Yes.
So let me introduce about Dr. Akash Deep. Dr. Akash Deep obtained his PhD in the chemistry from IIT Roorkee in 2004. Dr. Akash Deep is a principal scientist at Material Science and Sensor Application Group, CSIO, CSR Laboratory, Chandigarh. His area of the research specialization is bio, nanosensors, energy storage materials, and environmental chemistry. Dr. Akash Deep worked as a postdoctoral fellow at Department of Chemical Engineering, Instituto Superior Técnico Lisbon, FT, Portugal. Dr. Akash also worked as a visiting professor at Hanyang University, Korea, and guest scientist at RWTH, Asian University, Germany. He has published more than 180 research publications in highly cited journals with 8,500 citations. 6 book chapters, and delivered more than 120 presentations in national as well as international conferences. He has supervised 8 PhD scholars, and currently 8 students are working with him. He has also filed 2 patents. He has completed 5 R&D sponsored projects from different funding agencies like CSR, DBT, DST, and 4 projects are still going on. He has transferred 4 technologies to the different firms like MS Nanocell India Private Limited, MS Axio Recycle Private Limited Delhi, and 2 more. Dr. Akashdi has received various research awards and honors in his research careers. So we have a long list, but I do not want to be act as a interfere between the participant as well as the speaker. So now let us invite Dr. Akashdi once again. Dr. Akashdi, over to Dr. Akash.
Thank you, Dr. Malik, and I also thank the organizers of this conference, of this short-term course, for inviting me to deliver this talk. I'm going to share my screen here. Is my screen visible?
Yes, sir, it is visible. You can keep it in full mode.
Yes, sure. Oh, sorry, it's the second lecture that I have to deliver today. Okay, so the title of today's of my talk is Nanomaterials-based sensors for different analytes. I would like to introduce you to the sensor concept. What are the sensors and why are they needed? Why they are gaining significance? The sensors, or in broad terms, we can also call them biosensors, because most of the sensors that I'm going to talk about today are depending upon the use of some biomolecule to provide them the specificity. So the biosensors are also known as point-of-care testing devices. They are very much useful in today's scenario, both in environmental and clinical parameters, because of the features that they provide. The point-of-care testing, POCT, or biosensors are also known as bedside tests, near-patient test, or decentralized testing. The idea is not to take to the patient to the lab, but to bring the devices close to the patient or to the site of analysis. So the tests are conducted with the help of biosensors at the site of the patient care, and they provide rapid test results leading to faster patient treatment. We don't have to wait too long for the results to come from the clinics to your emails or to your doorstep, but with the help of these biosensors, you can immediately get the results. They can be performed at the patient location even by the non-laboratorians. You don't need any trained person, only some basic training, and you can get the device working. And these types of biosensors are very useful in easy environmental monitoring also, when you have to monitor the quality of water or the quality of your air, as well as the quality of your food samples. So for those type of applications, the biosensors are gaining the prominence. And what are the forces that are making this to happen? One is population. Because of the increasing population, we need more and more testing. And for more and more testing, we need less and less dependent upon the labs. So one of these factors is driving the emergence of biosensor market. Then knowledge. The knowledge about the nanomaterials, the knowledge about the modern technologies, all this is ultimately culminating into the development of modern devices that can help us getting the tests done at our own location. And of course, the economics. The economics, because this is also important. Normally, the tests at labs are very expensive. So at tests which cost around 100 rupees at the lab, with the help of biosensors, you can also get them done in around 10 rupees. So all these forces are changing the convention techniques, and they are bringing more the significance of biosensors commercially as well as personally. What are the advantages of POCTs? They need very small sample volumes. We don't need to get mLs of volume, but microliters will also work. unprocessed specimen, the raw samples can be tested with the help of devices. So there is no need to process the sample, and this saves a valuable time. Then they are portable, and they have a wide menu of analytes available. With the increasing technological innovations and invention, various types of analytes ranging from clinical parameters to environmental parameters to food quality parameters. Now the devices are available for those also. Because the tests are done at the site, so we have reduced potential for sample deterioration. We don't need to carry the sample to the lab, which might take hours. And in those hours, the sample might get deteriorated. So the sample is collected and tested at the site itself. So we have a reduced potential for sample deterioration. They accelerate the diagnostic and therapeutic process because we have the results available within minutes. So we can start the diagnostic processes as soon as possible. They are very easy to use, and they enable the caregiver or healthcare provider to report changes in the patient condition. So monitoring becomes easier. We can get the results after whatever the therapeutic action has been given to the patient, and that result can decide what next action has to be taken. But this slide defines what are the biosensors in broad terms and what is their definition. By definition, the biosensors are the self-contained integrated devices that are capable of providing specific qualitative or quantitative analytical information. So both type of information, qualitative or quantitative. The difference is in qualitative, you just come to know about the presence of a particular analyte. For example, you want to know whether I have some problem in my blood. For example, is there a cancer antigen present? Yes or no? It can give, as well as how much is the concentration. That is a quantitative information. So both types of information can be obtained with the biosensor devices, and they essentially contain a biological recognition element, because this element is required to provide you the specificity of detection, and this recognition element is in direct spatial contact with the transstructure element. So this all can be understood in these figures and text here. The samples that we can analyze with the help of biosensors could be human samples like blood, urine. They could be food samples, juice samples, and they could be environmental and agriculture samples. These are just the examples. Many other kinds of samples could also be analyzed. So what we do, we take some sample and we let the sample to interact with some biological element. The idea is to provide the specificity. A sample may contain different analytes. It may contain urea, it may contain glucose, cholesterol, but ultimately if we want to test only the glucose, we want our test to be specific from glucose. The other elements like urea or other materials should not interfere with the test. So for that, we need some biological elements. So these biological elements only react with the sample with the analyte that we want to test. For example, an enzyme like glucose oxidase, it only reacts with glucose, so it provides the specificity. Then there are antibodies, there are aptamers. So these are the biological elements which provide the specificity in the detection. Then after the reaction, then we need to detect what has happened during this reaction, whether we have some electrochemical changes or optical changes or colorimetric changes, mass changes. So reaction will lead to some changes. It might lead to the change in the electrical conductivity, or it might lead to the change in the color, or it might lead to the change of the mass of the product. So all these changes have to be analyzed with the help of transducers. And then signal processing, signal amplification, all this is done in this biosensor unit. The biosensors are very much useful for environmental monitoring, for the detection of gases, heavy metals, pesticides, water, then medical industry like glucose, cholesterol, proteins, toxins, cancer biomarkers, food sector, for quality assurance, microorganism detection, toxins, and also in defense sector when we want to detect biological warfare agents such as SARS, Bacillus anthracis. nowadays COVID also, it can be detected with the help of very portable biosensor systems. PCR is a method which takes 6 hours, 7 hours with biosensors. The antigen test kit, it provides the results within minutes. There are some important biosensor terms which are generally used. First is the analyte, what we want to detect. So analyte could be any molecule, protein, toxin, peptide, vitamin, sugar, metal ion. So this is what we want to detect. Then sample handling, because an analyte could be complex mixture. So the idea is to deliver the analyte to the sensitive region, because any sensor will have any sensitive region on which the sample has to be placed. So the sample handling is done with the help of some microfluidic channels. This microfluidic channel, it plays the role in increasing the concentration or decreasing the concentration as per the calibration curves, and it also can play a role in filtration or selection of analytes. Then comes the detection or recognition. So how will you specifically recognize the analyte? That is the term detection. It defines the mechanism how the specific recognition is taking place. And then signal, how do we know that there was a detection? So there is a change in some property during the reaction, and that is recorded with the help of some electronics or amplification circuits. There are some desirable characteristics in biosensors which must be met when we are developing some devices. And these characteristics are nowadays met with the help of advanced materials. I give some examples that high sensitivity, because not every sample has the presence of the analyte in high concentrations. Most of the time, it's in nanomolar to femtomolar range. And generally, the instruments like HPLC or chromatographies are used to achieve such kind of sensitivities. But with the help of advanced materials, the biosensors have been developed which can match the performance of those conventional systems. Then specificity is one of the parameters that is very much required, because we don't want the other targets to influence our test. We only want to detect the element what is needed for us. Rapid analysis, we want the test to be done within minutes. It should be low cost, should be portable, should provide accuracy, reproducibility, and it should handle the low sample. And these characteristics of sensors are met with the use of advanced materials mainly as transducers, because the signal that we collect, if the material we have can collect the signal to that low level, then we can obviously achieve high sensitivity. And apart from high sensitivity, the specificity is also dependent upon the selection of material that we use to make our sensors. So these are some of the advanced materials that are used for the fabrication of sensors: metal nanorods, metal nanoparticles, carbon nanotubes, and graphene. Then we have conducting polymers, quantum dot. Nowadays, the transition metal dichalcogenides, including MOS2, that is molybdenum disulfide, tungsten disulfide, and other TMDCs, are gaining very much prominence because of some of the advantages that they provide over other types of materials. And then metal organic frameworks are also very interesting option. Then this MXenes, two-dimensional metal carbides, are the latest entry in the market of advanced functional materials, and these are gaining a lot of significance during the last few years for different applications, including sensors. And these are some of the analytes that can be, in fact, those have been developed in our lab. For example, cancer markers, prostate-specific cancer marker, HER, PR. These are also breast cancer markers, estrogen receptor. Then cardiac markers, which allows the detection of heart attack in real time. So this is biomarker, myoglobin, troponin I, then pesticides like methyl parathion, atrazine, heavy metals, nitroaromatics. So the idea is to give you an example that we can detect so many range of analytes with the help of biosensors. There are some special properties of advanced transduction nanomaterials that help us in achieving better characteristics of the sensors. So most of the advanced materials are listed here that are being used now these days in modern biosensors. Quantum dots, very tiny nanoparticles of the range of less than 10 nanometer. Then we have carbon nanotubes. These could be single wall carbon nanotubes or multiple wall carbon nanotubes, depending upon the analyte that we want to detect. One can choose whether we want to use single wall or multiple wall. Then we have a very nice material here, 2D graphene. This is a very important material in the domain of this 2D nanomaterials. We have MOS2. Then core nanoparticles are basically one of the most widely used nanoparticles for the fabrication of biosensors because they are also FDA approved. Then dendrimers. I will cover some of these nanoparticles in today's talk, and these nanomaterials have been explored in our laboratory for the development of different kind of biosensors. So one of the material that I would like to discuss today is metal organic framework. The metal organic framework is a hierarchical chemical structure, and they are porous. Basically, they are coordination polymers. They are polymers and porous. So here you can see that when we talk about the difference between coordination compound and MOF, this simple figure explains you the difference. Metal center plus chelating agent, it will lead to the formation of coordination compound. But if we have a diverging ligand, then what we ultimately achieve is a framework which has the pores in its structure, and this framework is repeated to form the polymers. These frameworks are the crystalline network of metal ion coordinated to multidentate organic molecules. So we have one metal ion and one multidentate organic molecule, and these are then forming a coordination complex. The features of such type of structures are listed here. They are organometallic compounds and they have pore selective functionality. The explanation of this pore selective functionality is that we can have different diverging ligands with different length here. So if we change this length or the geometry of this diverging ligand, then what we'll achieve? We achieve different pore sizes here. So you can see that window here, it has a particular pore size, but by changing the length of this ligand, we can make a selective pore size of this framework. And this selectivity is very much important to capture specific molecules. For example, if I want to capture oxygen here or hydrogen here, I can take a diverging ligand which has a length similar to the oxygen or hydrogen molecule, and by choosing that length, I will be ending up fabricating one structure which can only selectively capture hydrogen or oxygen. So this is the pore selective functionality, which is very, very important in the field of metal organic framework applications, in catalysis, in gas capture, in environmental application, in sensing as well. They have very high surface to volume ratio. In fact, MOF material has the world record in powder specific surface area, 7,800 meters square per gram. So here the comparison is given that graphene, which is very well-known nanomaterial, if we take 1 gram of graphene, it takes around 3,000 square meters of area. But 1 gram of this DTU60 MOF, it will cover an area of 7,800 square meters. So you can see how much larger the surface to volume ratio, area ratio of the MOF is. Then they are highly temperature stable. They are stable up to 300 degrees Celsius, 400 degrees Celsius. Their structure remains intact. They also have low desorption energy. So in sensors or in any applications, this is very important, because once you utilize this molecule for the capture or for the sensing of any analyte, you also need to regenerate it for multiple uses. So once it captures something, then we should also be able to get that analyte released from the molecule, so that it can be reused again. And this low desorption energy means we can also get the analytes out of this structure using low energy. And this provides a very commercial feasibility and viability to this type of structure. They are non-toxic with biodegradability properties. They can also be injected within the body. So if you want to deliver some drugs, if we want to monitor what's happening within our cellular system, we can attach some special molecules and we can inject these MOFs within the body, and with the help of fluorescence microscopy, we can track where these structures are going, where these structures are binding. So all those disease diagnosis can be done with the help of these MOF structures. They have a stable fluorescence, and they have availability of large number of organic functional groups for improved biosensing. For biosensing, as I discussed in one of the previous slides, we need some biomolecule that can provide the specificity, and that biomolecule is attached to the structures with the help of functional groups. And because we are using organic ligands here, that's why we have a number of functional groups available over which we can target or we can attach our enzymes or antibodies to get the formation of a specific sensor molecule. The synthesis of MOFs is also not very difficult like other nanomaterials. They can be prepared simply in lab by solothermal, hydrothermal, or layer by layer synthesis methods. The second material that I will discuss is molybdenum disulfide. So the molybdenum disulfide is a 2D layered material. Here you can see that this is MOS2 structure, and if we separate these layers, one MO and 2S, then it constitutes a 2D structure, MOS2 structure. This is also a high surface area material, and this is widely spread naturally distributed material. So the cost of MOS2 is much cheaper than other nanomaterials like CNTs or graphene. It is a semiconductor material with a direct band gap of 1.8 eV for single layer and indirect band gap of 1.29 eV for bulk. So this property can be used to fabricate the sensors, and it has a high electron mobility of around this value. Synthesis of MOS2 can also be carried out in lab by various methods. Here some of the methods are shown: chemical vapor deposition, and we have chemical exfoliation, a very simple scotch tape assisted mechanical exfoliation. This is very widely used. We just take bulk MOS2, and then with the help of scotch tape we keep removing the fine layers of two-dimensional MOS2. So this is a very simple method, yet it can provide the preparation of nano MOS2 in large scales. Then we have solvent-based exfoliation. We have laser thinning methods available. We have electrochemical synthesis methods available, the hydrothermal methods available, and sonochemicals. So all these methods can lead to the formation of nano MOS2 from bulk MOS2. Then this is another class of material that is emerging very highly useful in different applications: amazine. Amazines are basically a class of two-dimensional inorganic compounds. Here you can see the amazines are made up of basically these three: M, A, X, and P. So M could be scandium, titanium, vanadium, chromium. All these are listed here. Then this is A phase: aluminium, silicon, phosphorus, silicon, sulfur, gallium. Then X, C or N. And then T, we have here HOFCl. So the idea is to start this MAX phase. And MAX phase is used as a starting material, and then we reach out this A from this phase, max phase. So when we reach out the A, then it remains MX, MXP, MX. So different types of structures can be formed. And because of the availability of different M, A, X, and P elements, we could derive different forms of magazines. These materials are also few atom thick materials with layers of transition metal carbides, nitrides, or carbonitrides. The features of MOFs and other 2D materials as transducers in sensors could be summarized in these few points: that these MOFs and 2D nanomaterials, they can provide both optical and electrochemical transduction. They could be used as a fluorescence sensor, they could be used as an electrochemical sensor, and they fulfill the following important requirements. First, that they are readily functional for the efficient bioconjugation. To attach the antibodies or enzymes, we need some functionality over the materials, and in this case, we have the materials ready for that type of functionality. Then structural compatibility with recognition elements, proteins, phages, antibodies, nucleic acid. These are nanomaterials, could be tailored as micro particles also. So we can get different type of morphologies, sheet form, we can have particle forms, we can have triangle forms, and in from 1 nanometer to 1 micron. So depending upon what type of proteins or what type of antibodies or nucleic acids we are using, we can tailor the synthesis accordingly. Retention time for analytes. In many times, the analytes contains very low concentrations of these of the sample that we want to test, and in such cases, what we need a retention time so that the sensors remains in contact with the sample for long time, and they can allow the diffusion to their inner parts also, to their inner structure. So these are the porous materials. So the sample can diffuse into the vicinity of those active sites, and because of that, we achieve a better sensitivity in the detection. Processing suitability for the design of thin films with reproducible characteristics. Any device nowadays, it requires mostly thin film type of configuration. So the electrodes or any other types of chips for the sensors, rather than simple solution particle form, what we need, thin films. And in all these cases of MOFs and 2D nanomaterials, we can get this particular design of thin films by different methods. They have appropriate electrical activity and fluorescence stability, which is also useful for the sensor applications. So this is a pictorial representation how we can design a biosensor. Here in the first step, we synthesize our material. It could be MOF, it could be magazine, it could be other type of graphene or nanoparticles. Then this is then modified with the desired properties. As I told you that it should be containing some functional group. It could be sewage group, amine group, not just the material, but it should be functional. So that functionality is then provided with the help of post-synthetic modification or in situ synthesis modification as well. Then we attach some proteins or some biorecognition elements to these structures. Could be aptamers, could be DNAs, could be antibodies, enzymes, and these are done to provide the specificity to the sensor. Then these materials are grafted over some thin films or optical fibers, or they can also be used as a solution as well. So these are the devices, solid state devices. Otherwise, the kits with the solution form are also available or are also developed. Then here you can see that this device is then integrated with the suitable optical fiber units or some other types of electronics. The electrometric thin film sensor are also developed, and then we use those sensors for pesticides detection, for gas detection, for radiation sensing, for explosive sensing, pathogen sensing, different domains of applications. Now, interfacing of nanomaterials with biomolecules is one of the important steps, because this should be a robust chemistry. Once we decide what type of biomolecule is to be loaded on the nanomaterial, then a chemistry has to be decided. So both type of chemistries, covalent attachment and hydrophobic interactions, are available. So in this example, you can see that a nanoparticle, it is conjugated with the drugs, with RNAs, with aptamers, or with the other peptides, pegylated glycols, fluorescent dyes, carbohydrates, single-stranded DNAs, antibodies, through different covalent chemistries. So this covalent chemistry is a robust chemistry, and it provides a stable interaction between the nanoparticle and the biomolecule. Otherwise, we can simply have hydrophobic interactions. Hydrophobic interactions are useful when we are using hydrophobic nanomaterials. So some nanomaterials have contact angle of more than 100 or 110 degree. So those kind of nanomaterials can simply be brought in contact with these enzymes or aptamers, and because these biomolecules have some hydrophobic regions in them as well, so hydrophobic interactions takes place, and in such cases we don't need the use of tedious chemistries of covalent attachment. So both these types of chemistries are decided upon the type of nanomaterial and what contact angle the nanomaterial is possessing. So here again, some more points about the bioconjugation methods. We don't need to go in details. Enzyme-based sensors are very much in use for different applications. One of the most widely used enzyme sensor is glucose sensor that we use to detect diabetes from that. So in this case, the materials that are loaded on the electrode, they have to be integrated with some enzyme. So for glucose, there is an enzyme, glucose oxidase. So there are different methods by which we can attach the nanomaterial and enzyme. So some of the examples are demonstrated here. For example, we have a synthesized MOF. We can allow the diffusion of enzyme in that because this MOF is a porous molecule. Then we can simply mix the two solutions of enzyme and MOF. And what will happen? The enzyme will diffuse into the pores and it will provide you a structure. Then in situ encapsulation of enzyme within MOF, when we are synthesizing the MOF using organic linker and metal ion, we can also mix the enzyme into the solution, and when the synthesis will complete, it will have the enzyme loaded into that structure. The enzyme immobilization on the surface of MOF. So here within the vicinity of within the pores. Now second example is when you are synthesizing, and third example is on the surface. So this surface immobilization can be attained with the help of covalent attachment through activation and other dye tagging methods. So type of the sensor platforms that we are studying in CSI or CSIO Chandigarh here are of different types. We have screen printed electrodes. These are very low cost electrodes, and we fabricate these electrodes with the help of screen printing technology in our lab itself. So the cost of one electrode, if we purchase it from market, it is around 100 rupees, but when we are printing them in our lab, the cost is very low. It is around 2 to 3 rupees. And then this, you can see it, this electrode has three areas. One is working area, counter electrode, and a reference electrode. So we modify this working area with the nanomaterials, 2D nanomaterials or other type of composites. And then with the help of electrochemical measurements, we use these sensors for the analysis of different biomarkers. For example, troponin, prostate-specific antigen, glucose, hemoglobin, etc. These sensors have very low detection limit. They can detect up to nanogram per ml or femtogram per ml, and they are easy to dispose. So they are use and throw type of sensors. Then we have interdigited electrodes also in our lab. These interdigited electrodes are fabricated with physical patterning techniques, and the beauty of these interdigited electrodes is that on a single chip we can carry out the analysis of multiple parameters. So these are for one analyte, but these interdigited electrodes, the single chip can be used for multiple analysis. So these they have some microelectrodes fabricated over them, and these microelectrodes are then modified with nanomaterials, and they are applicable where we do not want to use biocombination elements because they are very sensitive devices. So in this case, we use them for the detection of antibiotics, for the detection of pesticides, etc. Then we have also developed some printed thin films and optical fiber-based sensors. So these printed thin films are formed with the help of inkjet printing kind of technique. So we make our material, so in solution form, we fill it in the cartridge of an inkjet printer, and then we print different patterns using simple printer available in the market. So these patterns are of nanomaterials. These are fluorescent patterns, and when they come in contact with some gases, they change the color. Likewise, optical fibers can also be modified with the nanomaterials, and then these optical fibers can be studied with the help of grating-based devices or SPR-based devices. These type of materials, these types of sensors we have developed with MOF and MOS materials, and they are very good optical analytical methods with solid-state properties. Apart from these solid-state devices, we can simply use solutions. So we prepare the solution of some nanomaterial before. You can see that before the test of some particular analyte. In this case, a bacteria was tested. So before adding the bacteria into solution, it was like white color, and once we added the bacteria into the solution, it detected the presence of bacteria and it turned blue. So these are the buffer suspended materials, and these are also the optical analytical tools and available in the form of liquid kits. Some more examples of thin film sensors, how they are used. Here this is shown for the detection of ammonia. So different type of MOFs could be copper MOF or cobalt MOF. MOFs are basically the combination of organic and metal ions. So here I am representing that in this case the cobalt was the metal ion that was used to form this MOF. In this case H+, it was copper, and then in this case it was iron. So you can see different patterns have been developed using inkjet printing techniques, and when they come in contact with ammonia, their fluorescence is changing. So this is a very simple method to detect the presence of ammonia in the environment, and it's very highly sensitive. So it can detect ammonia from 5 ppm to 80 ppm. Then this is a typical design concept of an electrochemical immunosensor. How we develop the electrochemical immunosensor: we take our material, nanomaterial, we drop cast it onto some surface of the electrode, working in the area of the electrode. Then we modify that material film with antibodies, and then it becomes applicable for the selective detection of bacteria. And here you can see that we can use amperometric detection methods or impedance spectroscopic based methods for analyzing the reactions that are taking place between the sensor and the analyte. Then this is an example about how the liquid-based sensors, liquid-based solution form-based materials can be used as sensors. So one of the examples shown here. In this case, one MOF was synthesized by mixing terbium nitrate and this H3BTC again, simply by stirring. Then it led to the formation of this complex TBBTC. It's a nanorod type of complex and it shows green fluorescence. We then modify it with antibodies which are specific to this E. coli bacteria. And when the E. coli bacteria comes in contact or it's mixed with this solution of TB-BTC MOF, then it leads to the quenching of the fluorescence. Here you can see that different colonies and different concentration of the bacteria, they cause different extent of quenching in the signal of this fluorescence. So this is a very simple way of detecting what is the concentration of bacteria in a solution, in a sample. In this case, we tested some juice samples and milk samples, and we were able to detect the presence of bacteria to as low as 13 colonies per ml. This is the how the bacteria is interacting with our nanomaterial. It's shown here. So we have these small rods. You can see small rods. They are modified with the antibodies, and these bigger rods are basically the bacteria that have been captured by our nanomaterial, which is immobilized with the antibodies. Liquid-based sensor. The example of another liquid-based sensor is shown in this work here. Methylpyethon is a pesticide. In this case, MOF material. Again, this was a terbium MOF. It's a green material, green fluorescent material. It was modified with this enzyme OPH, organophosphate hydrolase. When this whole compound comes in contact with the pesticides, it leads to the formation of another compound, PNP, paranitrophenol. And this paranitrophenol has a specific UV visible absorbance peak at 410 nanometer. So just by recording the UV visible spectra, once we mix these pesticides with our sensor material, we can detect what is the concentration of this pesticide in the sample. So this type of sensor has also been used for the detection of pesticides in water and food samples. This is just to show that this very simple solution based sensors could be very sensitive as well. So the limit of detection of around 1 nanometer with high specificity has been achieved in this case. And this compound was reusable for 8 cycles. Once it was used, we can centrifuge it, we can recover it, and again reuse. So it was reusable for 8 cycles, and it was stable up to 80 days. Then some of this slide is showing another example how MOF can be used for the detection of another bacteria. I can skip this because of short time. Now this slide shows how a sensor chip can be used for the multiplex biosensing. So on a single chip, we can detect 2 bacteria, E. coli and S. aureus. So these are the AFM images showing how this chip was modified with our nanomaterial. It's like a very spiral type of nanomaterial that was loaded with the help of physical methods over this chip, and we use this chip for the simultaneous detection of 2 different bacteria. Then we have used different types of MOS2 nano materials, including nanosheets, quantum dots, or composites, to form different type of sensors, and these have been conjugated with antibodies using different chemistries. So some of the slides I can skip because I don't have much time here. That just to show you that MOS2 based sensor is a simple device to detect the concentration of prostate specific antigen and bovine serum antigen. These nanomaterials are synthesized with the help of different technologies using XRD or UV visible spectra. So you can, here in this AFM analysis, you can see very fine AFM, very fine sheets have been formed with a layer thickness of around 10 to 15 nanometer. Then we characterize them with cyclic photogrammetry. I can show you the response here. This is the response of this sensor, how this sensor is responding to the presence of bovine serum albumin. You can see that with different concentration, the current of this sensor is changing, and this is linear within 0.01 nanogram per mole to 10 nanogram per mole. So sensitivity of this sensor is very good. And likewise, the sensor was also used for the detection of prostate specific antigen. In prostate specific antigen, we could detect the presence of this cancer marker to a very low level. And this type of sensors are also useful for the detection of these markers in serum, in blood samples. So in blood samples also, we have tested them, and we found that the recovery, means the performance, is within the acceptable level. Then other types of MOS2 morphologies like quantum dots have also been used for the detection of prostate specific antigen. Here in this slide, I'm showing how these quantum dots were characterized by TAM, AFM, and dynamic light scattering techniques to confirm that the formation was in the nano range. Impedance-based analysis, it provided us a way to detect the presence of PSA, that is prostate specific antigen, from 0.01 picogram per ml to 200 nanogram per ml. So very, very low detection limit has been achieved. And this is specific in presence of various other analytes also. Here in this particular figure, you can see that the sensor is giving response only to this PSA, the black one, and it's not giving response to other markers that could also be present in the same sample. This is one of the work that we carried out to synthesize MOS2 nanosheets using electrochemical intercalation method. In this work, what we did, we synthesized the MOS2 nanosheets from MO metal sheet. This MO metal sheet was used as a negative electrode, and in this 3-cell configuration, we allowed the sodium to intercalate within this molybdenum sheet, and then this ultrasonication assisted exfoliation was used to derive these very fine nanosheets of around 2.7 nanometer thickness, and then a field effect transistor based sensor was developed. So here you can see by this method we could achieve the formation of nanosheets to this layer thickness of around 2 nanometer. TAM also confirmed the same thing. The around 7 sheets were formed with a total thickness of around 2.3 nanometer. And then these sheets were used to modify these field effect transistors. So these field effect transistors are also having different sensing regions. So these devices can also be used for a single chip can be used for around 16 to 20 analysis. We don't have to reuse different electrodes for different concentrations. So single chip can be used for multiple analysis. In this case also, we achieved a very good calibration curve here. You can see that the PSA could be detected from this low concentration, 10 to the power minus 5 nanogram per ml to 75 nanogram per ml. This is specificity test. So we confirm that this is only giving response to the desired antigen. So I can skip all this. And this is just to show the amazine-based biosensors, how they can work also. In this case also, we can take the field effect transistor-based devices. We can modify these field effect transistor-based devices with our amazines. And when this type of sensors comes in contact with some sample, here in this case cells, they then interact with the target molecules, and then what we achieve, what we observe the change in the current as this device comes in contact with the sample. So I can conclude my talk with these important points that MOS and 2D nanomaterials, they provide high sensitivity for the biosensing applications because of the characteristics that I discussed in the slides, like large surface area and orderness in the structure. So this orderness in the structure is useful because we want the characteristics to be reproduced. So if we are able to synthesize a nanomaterial which is ordered in structure, means we can reproduce its characteristics. Then they have large surface area. So this large surface area leads to the improved sensor sensitivity. They are structurally compatible with different biorecognition elements. And we also have the regeneration possibilities with them. So a sensor, once it is used for a particular test, we can also regenerate it for multiple cycles. The sensors can be converted into sensor papers, sensing kits, stripes, and other types of electrodes. So different type of configurations can be made with the help of these nanomaterials, 2D nanomaterials and MOS. So I acknowledge my PhD students who have done their research work in the area of sensors using 2D materials and MOS. I also acknowledge the funding from different funding agencies like CSIR, DST, and DBT, and I thank my director for providing all the infrastructure facilities. Thank you very much, and I'm now opening this for the questions.
Thank you, Dr. Akashdeep sir, for this articulate and quite interesting talk on one of the emerging topic, nanomaterial-based sensors. I hope all the participants get benefited by this highly informative interaction. I again invite participants for their queries. Participants, please ask the question directly to Akashdeep sir.
Sir, good afternoon, sir. Excuse me, sir. Am I audible?
Yes, you're
Hello, sir. Sir, I have one doubt with respect to the sensitivity of the sensor, sir. How long this material will be sensitive? Is there any time limit or a material character based?
Okay, you are asking about the shelf life, I think.
Yes, sir.
Okay.
Material, yeah.
Yeah. So we test the shelf life of these materials for around 6 months to 1 year, because they are with us in the lab and we keep testing them again and again after 1 month or 2 months or 3 months. So what we have observed that these nanomaterial sensors are basically stable for at least up to 6 to 7 months. Most of them are stable, and in some cases, like in MOF-based sensors, they are stable up to 1 year. So we only publish anything once we guarantee that this material is basically is having a good shelf life. It's stable for long-term use. Then only we can conclude that this is a useful sensor. Otherwise, if a sensor is not providing stable results during the course of time, then it's of no use.
Okay, sir. Thank you.
Yeah, thank you.
If no other query, then once again, on the behalf of organizing team and NIT Zay, I would like to thank Dr. Akash Deep and Dr. S. Krishna Prasad sir, the speaker of the first day of this STC. I also thank all the participants for their valuable presence. So now we end the today's session and we will meet tomorrow at 10 a.m.
Okay, thank you very much.
Thank you so much, sir.
Thank you.
Thank you, everyone.